Okay, so this is a problem about a diatomic gas, sorry, a monatomic gas. So it's got gamma equals 5/3, right? The number of degrees of freedom is 3, and the number of moles in this gas is 3. And so this gas undergoes a cycle. You can see it drawn here. This is a PV diagram. Notice the units for pressure are atmospheres, and the units for volume are liters. I'm going to talk about that more in a second. So this gas is undergoing a cyclic process. It goes from A to B, this is isobaric. And these two guys, let me see if I can draw a little red arrow. This one and that one are adiabatic. Right? These guys are isobaric. Right? And it undergoes this cycle. We want to calculate P, V, and T at every point. Notice you get some of them. So the pressure at A and B is 4 atmospheres, and so I'm just going to fill that in here. I'm going to say the pressure at A is 4 atmospheres, and the pressure at B is 4 atmospheres. The pressure at C is 1 atmosphere, and the pressure at D is 1 atmosphere. Right? I know a few other things. The volume at A is 4 liters, and then the volume at C is 20 liters. And so the first thing I want to do, my job is to figure out all of the other blanks in here, right? And so if we look at position A, I want to say one other thing. Notice the units on here. Normally we're doing units of pascals for pressure. We do SI, pascals for pressure in cubic meters. This is liters and atmospheres. It turns out you can write the gas constant, which is 8.314 joules per mole Kelvin. It's also equal to 0.08206 liter atmospheres per mole Kelvin. Notice a liter atmosphere is a volume times a pressure. That's an energy unit. And so when you get a problem that's got pressure in atmospheres and volume in liters, often you'll just stick with the liters and the atmospheres and as your energy. A liter atmosphere is a unit of energy. And you'll just use this form of the gas constant instead of this one. We could go through and transform units and you would see these were the same if I converted liter atmospheres into joules. So if I want to calculate to fill out position A, the only thing I don't know is T, and I can use the ideal gas law and say, look, the temperature at A is equal to the pressure at A times the volume at A over NR, right? And that's equal to 4 atmospheres times 4 liters divided by 3 moles times 0.08206 liter atmospheres per mole Kelvin. And if I evaluate that, I get TA is equal to, what do I get? 65 Kelvin, if you work that out. And so that gives me, I'll just keep it in red, I guess, 65 Kelvin. The next easy one to do is C, since I can just do the same thing for C, and so I can say for point C, TC is equal to PC VC over NR, which is 1 atmosphere times 20 liters over 3 moles times 0.08206 liter atmospheres per mole Kelvin. And that's equal to, the number I get for that for C is about 81.25. I'm not being very consistent about my significant figures here. And so I'm going to put here, I'm going to put 81.25. Now it's a little tricky. Now if I want to do like D, I have to do something a little more sophisticated because I can't just grab the ideal gas law because I have two unknowns in it. I know P and I know N, but I don't know V and T. And so this is where I use the fact that B to C is an, or A to B, no, sorry, B to C is an adiabatic curve. And so I can say PB VB to the gamma is equal to PC VC to the gamma. It's because it's adiabatic. That was an exclamation point, not a very good one. All right, let me try again. There we go. And so now in this equation, I know everything but VB. And so I can say VB to the gamma is equal to PC over PB VC to the gamma. Sorry, I'm doing B here. Right. I'm trying to figure out this point here, write the data for that point there. And so in order to get VB by itself, I raise both sides to the 1 over gamma. So I say VB to the gamma to the 1 over gamma is equal to PC over PB, VC to the gamma, all to the 1 over gamma. And that gives me VB is equal to PC over PB to the 1 over gamma times VC. And now I can just put numbers in this. PC is 1 atmosphere. PB is 4 atmospheres. 1 over gamma, and gamma is 5/3, so 1 over gamma is 3/5. And then V sub C is 20 liters. And so I get VB is equal to 8.7 liters. That ends up being 0.25 to the 0.6, which is like, I forget, it's like 0.43 or something, and then times 20. And so that gives me in this spot, that gives me 8.7. And now I can find the T. I can say TB is equal to PB VB over NR, and that's equal to 4 atmospheres times 8.7 liters over 3 moles times 0.08206 liter atmospheres per mole Kelvin. Sorry about the tiny font, right? And what I get for that is about 141.4 Kelvin. Something like that. And so I've got to make myself a little more room here, as you can probably see. Let me pause this so I can get something to make more room with. So now I can evaluate these guys, and it's basically the same process. If I look at D instead of B now, I have the same thing. D is on an adiabatic curve with A, and so I can say PD VD to the gamma is equal to PA VA to the gamma. And then I can say VD, which is the thing I'm going to get first, is equal to PA over PD, VA, sorry, this should be gamma, to the gamma, right? And if I do the same process as I just did here, I get VD is equal to PA over PD to the 1 over gamma times VA. And that's equal to, so the pressure at A is 4 liter atmospheres. The pressure at A, let me try that one more time, is 4 atmospheres divided by the pressure at D, which is 1 atmosphere, times the volume at A, which is 4 liters. Oh, this is to the 3/5, because it's to the 1 over gamma, and again, gamma is 5/3, and then times VA, which is 4 liters. And what I get when I do that is V sub D is 9.2 liters. And so that gets me a 9.2 here. And then I can say temperature at D is equal to pressure at D, volume at D over NR. And that's equal to 1 atmosphere times 9.2 liters over 3 moles times 0.08206 liter atmospheres per mole Kelvin. And that gets me to 37.4 Kelvin. So that calculates all the relevant parameters for the for pressure, volume, and temperature at all the points. And now what I'm going to do in this problem is determine the work. So I'm going to fill out this chart. I don't know if I can make it as clean. But I'm going to draw another chart down below where it's going to be, so let me just draw a line here, right? I'm going to have to make this one a little smaller and leave myself a lot of room. So I'm going to calculate the change in E internal, and then Q, and then W for the process A to B, B to C, C to D, and D to A. And so I've got all the relevant information in this, and I'm just going to try to calculate it over here. And so let's see if we can do that. Hopefully you can see what I'm doing, right? Let's just do them in order. And so we'll start with, let me get a black pen. We'll start with the process going from A to B. And we'll say the change in E internal is equal to N CV delta T, which is equal to N times 3/2 R, right? Because it's a monatomic gas, and so D is 3, and so it's 3/2 R delta T. That's equal to 3 moles times 3/2 times 0.08206 liter atmospheres per mole Kelvin. I have to write a little bigger. Times the temperature difference. It's temperature at B minus temperature at A, so it's 141.4 minus 65. I should put a little Kelvin on that. Minus 65 Kelvin, right? And so I get the change in E internal for that one is 28.2 liter atmospheres, right? The moles cancel here and the kelvins cancel there, and what I'm left with is liter atmospheres, and that's good because that's a unit of energy. That's the thing I want, right? And so I could fill this one in, 28.2. I should note that some of this you can fill in already, right? What is Q for B to C? Think about that for a second. You can pause it if you want and see if you can figure it out, but the answer is 0 because it's adiabatic, so the Qn is 0. Same thing for D to A, 0, right? And so now, the next thing I can do is for A to B, I can calculate the work, right? And that's equal to the integral of P dV, again, going from A to B, but the pressure is constant, and so that's just equal to P delta V, which is just the pressure, which is 4 atmospheres, times 8.7 liters minus 4 liters, which comes out to 18.8 liters, right? It's the pressure, they're at constant pressure. It's just the area under this, if you want to call it that, right? And so it's 18.8 liter atmospheres. Oops. Right. And so that's the work done. And again, the gas is expanding, so it's doing positive work. And so now we can calculate this thing, right? It's if I could say the change in E internal equals Q minus W, or Q is equal to the change in E internal plus W, and that's equal to 28.2 liter atmospheres plus 18.8 liter atmospheres. And what I get for that is 47. If I wanted to, I could calculate this differently. I can calculate this Q by saying, well, it's a constant pressure process, and so it's just NC sub P delta T. That's the heat capacity at constant pressure. That's what Cp is. And the Q is just NCP delta T. That's just 3 moles times 5 halves, because Cp is 5 halves when Cv is 3 halves, right? Cp equals Cv plus R. And this is times, so the temperature difference is Tb minus Ta. And so that's 141.4 minus 65. Those are both in Kelvin. I lost an R there. Oops. 0.08206 liter atmospheres per mole Kelvin times, I'm just going to have to put the times down here. So it's, again, Cp is equal to 5 halves R. And so I had to put the R in here. That's what this thing is. And then I have to multiply by the delta T, which is Tb minus Ta. And so it's 141.4 minus 65, Kelvin, minus 65 Kelvin. And you'll find if you do that, you also get 47 liter atmospheres. It's a nice check that you can do on some of them. You can't always calculate Q because it's not always in a clean, it's hard to calculate Q for some process, harder than for some process than for others. This happens to be a constant pressure process, And so it works okay. And so that gets all of those guys. All right, now we're going to do, now we're going to do B to C. And so I'm just going to have to, you're just going to have to freeze it and go back to it if you want to see it again. Right, and so we'll do B to C. Uh-oh. I feel like I've got a loose pin out here somewhere. Once again, the change in E internal is equal to NCV delta T. That's equal to 3 moles times 3 halves times 0.08206 liter atmospheres per mole Kelvin times the temperature difference, which is temperature at C minus temperature at D. So it's 81.25 Kelvin minus 141.4 Kelvin. I'll do this a little better. Is equal to what I get for that. I've completely lost my place here. It's a negative, right? Because that number is bigger than that number. I get a negative 22.2 liter atmospheres. So this is, nope, try that one. Negative 22.2, right? And now this one is actually easy, right? Because if I write change in E internal equals Q minus W, then I get W is equal to Q minus change in E internal. Right. And that's just 0 minus change in E internal, which means this is 22.2. Keep grabbing the wrong marker. Right, and so that's B to C. Right, Q is 0 for that one. It would be tricky to evaluate W as the integral of PdV because the pressure is not constant, it's those adiabatic curves. And so since Q is 0, this is just really just the easiest way to do it. And so now I'm going to do C to D. I'm going to use up a little more of the horizontal space. And so once again, the change in E internal equals NCV delta T. That's 3 moles times 3 halves times 0.08206 liter atmospheres per mole Kelvin. Right, this is times, like that. Times, so it's temperature at D minus temperature at C, so it's 37.4 Kelvin minus 81.25 Kelvin, like that. And what I get for that one is negative 16.2 liter atmospheres. This process, the one I'm looking at now, C to D, is another isobaric process. And so I can calculate the work done for this process. It's equal to P delta V. And so I know what the pressure is. It's 1 atmosphere. And this is just the volume at D minus the volume at C. And so the volume at D is 9.2 minus 20 is a negative So it's negative 10.8 liter atmospheres for the work done. And once again, we can calculate Q, right? The change in E internal is equal to Q minus W. So Q is equal to the change in E internal plus W so Q is equal to the change in the internal, which is minus 16.2 liter atmospheres, plus W, which is negative 10.8 liter atmospheres, which is that negative 27? So now we're at the last one, right? By the way, we could calculate Q the other way as well, just like we did earlier. Since this is a constant pressure process, we could say Q is equal to NCP delta T, and that's equal to 3 moles times 5 halves, because CP is 5 halves R, times 0.08206 liter atmospheres per mole Kelvin, times the temperature at D, which is 37.4 Kelvin, minus the temperature at C, which is 81.25 Kelvin. And if you evaluate all that stuff, you still get negative 27 liter atmospheres. So it gives you the warm fuzzy of getting the same answer you got just by elimination. And so now we'll do the last one. And let me make a quick comment about it before we get started. If you remember, if we go from A back to A, the total change in E internal has to be the same. And so technically, I could say, look, let me just write it this way. Change in E internal, A to B, plus the change in E internal, B to C, plus the change in E internal, C to D, plus the change in E internal, D to A, has to be 0. If I start at A and end at A, my total change in internal energy has to be 0. And so this says that the change in E internal, D to A, is equal to the negative of the others, minus change in E internal, A to B, minus the change in E internal, B to C, minus the change in E internal, C to D. And that means it's just the negative of these guys. So it's minus 28.2 liter atmospheres, plus 22.2 liter atmospheres, because I'm taking the negative of these guys and adding them, plus 16.2 liter atmospheres. And if you add all that up, you get 10.2 liter atmospheres. All those have to add up to 0. These two guys add up to 38.4. These two, negative 38.4. These guys add up to positive 38.4. Right, let's see. These are the work. If I say the change in E internal equals Q plus W, then W is equal to the change in E internal. Sorry, Q minus W. Then the work done is minus the change in the internal, which is minus 10.2 liter atmospheres. Dang it. And so that's your chart. This is all the pressure, volume, and temperature for this cycle. This is all the change in internal energy, Q and W. If you're looking at this as some kind of an engine cycle, which it could be, there are a few things you can say about it. The net work the engine does in one cycle is 18. Boy, that wasn't very good. Right? If I want to know the net work that this engine does in one cycle, the engine's doing positive work in these two places where it's expanding, it's doing positive work. When it's being contracted back to its original position, because the engine has to be going in a cycle, its work is being done on the gas. And so the net effect of that, these two guys, 18 and 22 is 40, and so this is 41 liter atmospheres. And 10.8 plus 10.2 is minus 21 liter atmospheres. And so this is W net, if you want to say, is 20 liter atmospheres in one cycle. That's the net amount of work my engine does. Part of the time my engine is kind of doing work on the gas, part of the time the gas is doing work for the engine. And so the net effect in a cycle is that. So the heat absorbed this is how much heat went in, right? This is how much heat went out. This, you don't usually talk about a net with heat. You blew this out your exhaust pipe, right? And so this is what came in from your gasoline when it combusted, the 47. This is the stuff you just didn't use. And so you just lost that heat. And so usually when you want to calculate the efficiency of an engine, it's equal to the net work divided by Qn. And so in this case, it would be 20 liter atmospheres divided by 47 liter atmospheres. This engine is 43% efficient. It's converting about 43% of that heat that it's absorbing into mechanical work. That's a pretty good engine. We'll talk more about this and do some other diagrams as we go.